Hey folks. So our lesson's going to look a little bit different today because I didn't do it when I was in school and I'm working from home today, so I'm doing it at 6 o'clock in the morning. Sorry about that. We're still going to get through it. We're going to be solving out rational equations today. And they're actually going to be really similar to solving out absolute value equations where you have to isolate the absolute value and then square both sides. Rationals are very similar. They're also very similar because you can have an extraneous solution and you can check by graphing. Let's get into it. So we're going to talk about how to solve radical equations here, and it's important to first talk about what a radical equation is. So it's an equation that has at least one radical term with a variable. If it doesn't have a variable in the radicand, meaning under the radical, it's not a radical equation. So let's take a look at this one, number 1. This looks like a radical equation. It has a radical, has a variable, but this actually is not a radical equation. The reason being is that variable isn't under the radical sign. That's an integer, not a variable. So we could solve this one out, but it's not a radical equation. Let's take a look at this one, number 2. This is a radical equation. You have a variable, x, underneath your radical sign, so that makes it a radical equation. Now, how to solve a radical equation out is this. It's actually really similar to solving out our absolute value equations. You have to isolate the radical, so isolate the weird part by inverse operations, just like we did with absolute value equations. Then you need to undo both sides, and here actually it's the same thing. You square them. Remember, you're probably going to have to use FOIL or the area method to do it and square it. We'll show examples where you do and where you don't. Then you solve as normal. And it's very important to check your work here, because just like in rational equations, where you could have an extraneous solution, here you could have an extraneous solution as well. Let's take a look at some examples. So here we have a radical equation. We have a lot of stuff under a square root. It's important to notice where the square root stops. This is all under our square root, so that's what we have to isolate. It's not alone on one side of the equation, because we have this plus 19. So I just need to subtract 19 from both sides. And then I'm going to wind up with an isolated equation. Cool. So we've isolated that. What we need to do now is square both sides, because we're moving down our checklist. So, important thing to keep in mind is I'm squaring all of this. And, well, this isn't all of anything, it's just an integer. Over on this side, we're going to have some cancellation. The square root and the square is going to cancel out. We're just left with 3x plus 37. Let me move that over to someplace where it's not blocking everything horribly. And over here, well, we know what that is. It's just equals to 64. From here on out, this is just a two-step algebraic equation. You've done them probably hundreds of times before. So let's solve it out quick. Check our work. There we go. We got our answer. And we can easily check this by plugging in over here and seeing. So this is my check. With these, it's important to do a check because you could have an extraneous solution. So I'm just going to plug in 9. So we got 3 times 9, so that's going to be 27. Plus 37, and that's all under my radical. Sorry folks, I'm doing this at home and I don't have my smartboard with me. So unfortunately, that's what you're stuck with. That's going to be 64. Square root of 64 is 8. But we know 8 plus 19 equals 27. Yeah, that checks out because you get 27 equals 27. So it works. We get a true statement here for our check. We're good to go. We have our next one here. So take a look at this. We have all of this under a radical. it's isolated on one side of the equation. So we can skip our first step here and just move on to our second, which is going to be to square both sides. So I'm just going to raise everything to the second power. Now notice, on this side, everything's going to cancel out nicely, and we're just going to be left with 5x plus 35. On this side, that's not going to happen. We're going to have to square it out using the area method. So keep that in mind. And when we square that out, we're going to get that. Now again, we've solved stuff like this in the past. What we're going to have to do is bring everything from this side over onto this side. Let's get to it. Going to make that equal to 0. My x squared is going to remain unchanged. I'm going to subtract the 5x over to here, so I'm going to get positive 9x. I'm going to subtract the 35 over to here, so that's going to get me 14. Well, we've solved this stuff out before. This is going to be a factors and sums because there's nothing in front of that x squared. So this is going to be x plus 7, x plus 2. So that means 0 equals x plus 7, 0 equals x plus 2. Let's give that some space. Well, that means x is going to equal negative 7. X is going to equal negative 2. Those are our answers. Now, we have to check them. So to do that, we're going to plug them back into the original equation. Now remember, my original equation didn't have any of the squares. So I got to erase that because I added them in. All I'm going to do, plug in negative 7 on both sides. Going to see what happens. Well, that means on this side I'm going to get negative 35 plus 35. The other side I'm going to get negative 7 plus 7. Well, on this side it's just going to become the square of 0. Equals 0. That checks out. Even though it's 0, we're good to go. It's a totally true statement. Now, let's check the other one. I'm going to copy my original equation. The only thing that's going to be different, instead of negative 7, it's going to be negative 2. Well, that means that over here it's going to be negative 10. Over here it's going to simplify this down to 5. Well, that means that this is just going to be 25. Well, we know that 5 equals 5. It's a true statement. It totally works. And let's show how this works in Desmos to give you a slightly different way of checking. I'm going to just type in the original equation. The left-hand side is one equation, the right-hand side is another. Now how you enter the square root in Desmos, you can either pull up the keyboard, and you can enter the square root symbol here, or if you want a shortcut, type SQRT, and then a square root symbol pops up. Either way, same square root symbol. So I'm going to type that as one side, x plus 7 as another. And where they intersect, the x values are our answers. And you can see this point has an x value of negative 7, this point has an x value of negative 2, and those were our two answers. So this works as a check. Let's go back and show one where you do have an extraneous solution. So we moved on to another one. This one is going to have an extraneous solution. I can't tell anyway by just looking at it. The only way I can tell is by solving it out, and I know because I've just solved this one out before. Either way, let's go through and solve. Isolate the radical by inverse operations. Well, this radical is already isolated. It's on one side of the equation by itself. We don't need to worry about that. Which means my next step is just going to be, nope. Which means my next step is just going to be this. Square out both sides. So take the inverse operation. Which means I'm going to be left with 25 minus 3x is equal to, and this is really similar to what we just saw. Cool. Well, we got to get everything by itself, so I'm going to subtract the 25. I'm going to add the 3x, so I'm going to 0 is equal to this. And then we just need to factor it out. Again, this is factor in sums because you don't have anything in front of the x squared. Oh, silly me, I messed up. So what we're going to have here is x minus 8 and x plus 3. Excuse me, minus 3. And when you solve it out, you're just going to get x equals 8, x equals 3. So let's check this and see what's going on. We're going to check it algebraically and we're going to check it graphically. So we're going to plug in 8 and 8, 8. Well, this is just going to be 24. This is just going to be 1. So it's going to come down to the square root of 1 is equal to the square root of 1, and we know that's true because the square root of 1 is just 1. So therefore, this checks out as an answer. Totally works. So let's try it with 3. Plug in the 3. That's going to be it. 9. This is going to give me negative 4. That's going to give me 16. That's going to give me a positive 4. Now, we're just relying on the principal square root here that we discussed. And this isn't true. Let's see what Desmos has to say about it and see if it backs us up. Thing as we did before, 25 minus 3x, x minus 7. These lines are only intersecting once, where x is 8. If we go over to where x is equal to 3, that's right here, the blue line and the red line are not intersecting in the same place. That's because when we're talking about this equation, we're just talking about the principal square root. That's why all of this is positive instead of negative. Because of that, even though you might be tempted to say that, well, this could be true. You know, you can have the square root of 16 be a negative 4 as well. I've done plus or minus 4. It won't work in this case. We're just relying on the principal square root. So we've seen one example where you isolate and you don't get an extraneous. You've seen one where you isolate and you do get an extraneous. You've seen how to check them. Let's check one that kind of breaks the rules a little bit and see how we can solve it. So we have this one. Now, you have probably already observed that we have a radical on the right-hand side and a radical on the left-hand side. Because of that, we can't do this first step of isolating by inverse operations. Even if I were to subtract this square root of x over to this side, it wouldn't all be under one radical. Because of that, we just skip to the second step and we square both sides. And it's going to be a doozy, but we got this. So what's going to end up happening is I need to expand this out using FOIL. Thankfully, on this side, it's just going to be x plus 6. These two are going to cancel each other out. Over here, it's not. I'm going to have this squared plus 4 times the square root of x plus 4. And I got all this by my box method or my area method or FOIL, whichever one you want to use, you're going to end up with that answer. So, we now need to simplify a little bit. This is just going to become x. And then we can move the x and the 4 over here. So if I subtract the x over, the x actually cancels out. That's weird. I subtract this 4 over, well, that's just going to be a 2. Then if I divide both sides by 4, I'm going to get 2 over 4, which is just equal to a half. If you want to put it as a decimal, that's fine. Well, at this point, we can solve this one out. You were able to solve this one out before you met me. Just square both sides and see what happens. On this side, you're going to just be left with x, and over here it's 0.25. Remember, half of a half is a quarter. And let's show how to just check this one using Desmos. Square root of x, make sure the 2 is outside of the radical. Square root of x plus 6, make sure everything's inside the radical. And we see 2 of these funny looking equations. They intersect right here. We can zoom in a bit to see their intersection point clearly. That's at 0.25. We're good to go. It works out. And if we zoom out, we can see that's the only intersection point. As these graphs get further and further to the positive side of the x-axis, they're staying, it looks like almost the same distance apart, so they're not going to intersect again. There's no hidden second intersection point. We've seen how to do it all. We've seen how to solve. We've seen the connections that it's had to the things that we've done in the past, and we know how to check it using Desmos, so as you are going through and solving, you can check before you hit complete on DeltaMath, and you know you got it right. Let's get into it, folks. Then you're going to complete those 3 DeltaMath problem sets, complete the summary, and you're good to go. Have a great day.